Okay, so now that you know how to solve this problem using prefix sums, in this video we will try to solve the same problem using segment trees, and we will also discuss the time complexity that we have for solving such problems. Okay, so let's just for the formality, let's read this problem again. You are given an array of n integers. Your task is to process q queries of the form what is the sum of values in the range a to b. Okay, and the first input, okay, so we have L and R values, and then we want to simply query, and just for the sake of um the introduction, let's say this is the first query. We need to print the range from 2 to 4. So these are the integers like 2, 3, 4. So when you sum these three integers, you will get 11. Okay, so I want to print something like this. Now when you are trying to use segment tree, okay, let's say we have, like, what is the segment tree? It is a range query data structure, and it is a very general data structure. So if you want to learn about range queries, you must know this data structure. Okay, now let's try to make a segment tree out of this. So we have 3 to, actually there are 8 nodes, so let me make a segment tree of 8 nodes. So what we have is, let's say we have a node here. Okay, obviously my the size of the array, so let's say a variable size is 8. Okay, so this is a node that we have. Now it will have 2 children. I'm going to keep increasing the number of children till the number of children just exceeds this number, okay, that we have. Like, let me just erase it for now. So what I'm going to do, let's say we have n equals to 8, and you will also realize why I'm doing it when I take some number that is not a power of 2. So what I'm trying to do is I want to make a complete binary tree till the number of leaf nodes is just greater than this number. Okay, so we will have one more level because this has only 2 nodes here. So let's have this. Right now also there are only 4 nodes, leaf nodes, and this number is greater than these 4 nodes, so we will go one more level down. Now sorry for the improper alignment, but yeah, this is what we have. Okay, now in this I will put all the numbers in the leaf nodes. Okay, so what do we have? We have 3, 4, 2, 5, 1, 1, 5, 3. Okay, so let me put the numbers in here. We have 3, 4, sorry, so we have 3, 2, 4, 5, 1, 1, 3, 2, 4, 5, 1, 1, and 5, 3. Okay, 5 and 3. Now how a segment tree is built is, let's say we have this, and now what I'm going to do is in the just upper level I'm going to put like 3 plus 2 is 5. So this node represents the sum of these 2 nodes. Okay, this node will represent the sum of these 2 nodes, so it is 9. This node will represent the sum of these 2 nodes, so it will be 2, and this node will represent the sum of these 2 nodes, so that is 8. Okay, now this node will represent the sum of these two, which correspondingly it will represent the sum of these 4 nodes. So it is simply 9 plus 5 plus 4, 9 plus 5 is 14. Okay, this node will represent the sum of these 4 nodes. Okay, so 8 plus 2 is 10, and this node, the root node, will actually represent the sum of entire array that we have, so it is actually equal to 24, right? So we will try to pre-compute it. Okay, so we will pre-compute it. And how much time do you think it will take to pre-compute this whole tree? I will give you some 5 seconds to actually think about it, and when you are done thinking, you can resume this video. Okay, so for those who are able to think about this, now let me just erase this part. What you will realize is that, let's say the number of leaf nodes that we have, I mean, for this case, since n was 8, the number of leaf nodes that we have was equals to the like for this case, since n was equals to 8, which is the perfect power of 2, we had n equals to the number of leaf nodes. But let's say the number of leaf nodes is sz, okay, a variable sz. Okay, Now this SZ, you will realize that the number of nodes here, like 1 2 3 4 5 6 7, is SZ minus 1, right? And the number of nodes we have is SZ. So approximately the number of total nodes that we have is 2 times SZ, right? So it will take you actually big O of n time to pre-compute the values for every node. So the building of segment tree takes big O of n time only. Okay. If you were not able to understand this, kindly try to count the nodes yourself. You can try making segment trees of different values, and you will realize this, that it will be the same answer. So it will take, so the building, so what we have here is that the building time of the segment tree is big O of n. Okay, so let me just write that down. Okay, so the building time of this segment tree is big O of n. Now, how do we query it? First of all, what you need to realize is that this node represents the sum of entire array. So let's say we have this node is position 0 1 2 3 4 5 6 7, and this 7 is not n minus 1, it is sz minus 1. Okay, sz is simply the number of leaf nodes that we have. Okay, so if you are here, uh, like this node represents the sum of a range. It starts from 0 and ends at 0. This 2 represents the sum, this node represents the sum from 1 to 1. Okay, this 2, this 4, this node represents the sum from 2 to 2, and similarly this goes on, like 3 to 3, 4 to 4, 5 to 5, and 6 to 6, and 7 to 7. Okay, and when we try to combine these nodes, this node will represent the sum from 0 to 1, 2 to 3, 4 to 5, and 6 to 7, right? And these two nodes, they will represent the sum from, like they will represent the sum from 0 to 3, and this will represent the sum from 4 to 7. Okay, and and the root node will obviously represent the sum from it will represent the sum from 0 to 7. Okay, so this is the complete segment tree that we have, and these values represent the sum from where to where the sum is inclusive values. Okay, in the range. Now let's say, like, we will try to simulate and find out the values of these queries using that segment tree that we have. So let's say I want the values, the sum of values from 2 to 4. Okay, so what we have is, let's say I'm starting from here. I want to know the values from position 2. So obviously this is 0 based indexing, so this is position 2, not this one. So position 2 to position 4. Okay, so what you need to do is, I will start from here, right? Now one way is to simply add these numbers one by one, so 2 plus 4 plus 5, but we will not do that. Okay, so let's say we have so I will start from the root node. Okay, one way. Okay, now there are two ways to query it. One is the recursive way and one is the iterative way. So obviously iterative version will be faster because there will be few recursion calls, few function calls, and that is why iterative version will be faster. But let's try to go with the recursive way for now. So let's say we start from here. We see that this node has the sum of values from 0 to 7, which is, and since the left node, like like we have a 0 here, right? So we don't need the part from 0 to 1. We don't need that, right? So what I will do is I will go left side. So let's go left. Okay, this still has the 0 to 1 part, so let's go more left. This still has, okay, so this part that we have, sorry, we don't really need the part from 0 to 0, right? So I will go left. Okay, so now going here, this side doesn't really make sense, so we will not take this part, we will go right in this case, because we are completely neglecting this part 0 to 0. And now this side, this node has the values from 1 to 1. Okay, so I will take this node, then I will go right side. Okay, I will see that we have 2 to 3. Okay, so this 2 to 3 is exactly in the range from 1 1 to 3, right? I want to query for range 1 to 3. First I got this value, that is 1 to 1, then I went right, I had this value 2 to 3. Okay, so I will take 2 to 3, which was completely inside this range. And once I have this value, I don't really need to go more down. Okay, I will go up, I will go right, I will see that this value is completely outside this range, and I will not return anything, and I will stop my execution here. So instead of adding these values 3 times, I only need to add these values 2 times. So which was 2 plus 9, that was 11. Okay, now I know I might have gone a bit fast. You can try to rewind this video and try querying it again. Okay, let's just try to query some more values. So let me go back a bit. Okay, so let's say the next query is 5 to 6, or let's take, no, not 24. I think I will just take some better values on my own. Let's say I want to query from 1 to position 5, 1 to 6. Okay, so let's say I want to query from position 1 to 6. So what happens is I start here, I see that this one is not completely inside this range, so I go left, still not completely inside this range, there is some unnecessary part on the left, so I will go more left, still not completely inside, I will go right. Now this value is completely outside the range that I want. This 0 to 0 is completely outside this range, so I will not return anything and I will go back. Okay, so let's say I will return some default value like 0. Okay, then I go right and I see that this value is completely inside this range, like 1 to 6. 1 to 1 is completely inside 1 to 6, so I will return this 2 value. So I will go up, I will say okay 2. Now I will sum these two values, so this will return 2 here. Okay, now I try to go right, I see that 2 to 3 is completely inside this range 1 to 3, 1 to 6, right? So I will not go further down, I will simply return 9 here. Okay, and then I will sum these two values and go up, like okay, this will return 11. Okay, then let's go right, I see that 0 to 7 was not completely, it has some unnecessary part, that is 7 to 7 part unnecessary here. So let's go right, let's try to go left, and I see that 4 to 5 is completely inside this range 1 to 6, right? So I won't go further down, I will simply return 2 here because we have this value, so 2. And now let's try to go more down because this edge is not processed, so I will go right, then I see that 6 to 7 has some unnecessary part, so let's go left first. Now this 6 to 6 is completely inside this range 1 to 6. Okay, so this will return 5, and then I go right, this is complete, like 7 to 7 is completely outside this range 1 to 6, right? So this will actually return 0. So 5 plus 0 is 5, so this is returning 5. 5 plus 2 is 7, so this will return 7, and now 7 plus 11 is 18, so we have our answer as 18. So that is how we query from segment tree. I think this was a good example, and we actually broke this whole 1 to 6 sum into how many parts? We broke it into 1 comma 1 plus 2 comma 3 plus 4 comma 5 plus 6 comma 6. Okay, like that. So since the height of this segment tree is obviously log 2 and log to the base n, log into the base 2, That is why this querying time will not take you more than 2 times login time. So your query time will be around login time. Okay, so that is how we query from the segment tree. Now let me just go back a bit. So let's just write this down, that our query time is big O of login time. Okay, so we have this segment tree. Now how do we actually build this segment tree? Like, we see that what we can do is when we have this, let me just go more back. When we have the segment tree, what I can do is initially, let's say all the values are 0 0 0 0 0 0 0. Okay, and when I try, like obviously since all the values are zeros, this will be 0 0 0 0 and 0 0. Okay, so what we can do is initially we will have all these values as 0, and currently this node value was 0, right? And when I try to put a 3 here, I will try to go up and update the sum values again. So this will become 3, then I will go up, 3 plus 0 is 3, and then I will go up and 3 plus 0 becomes 3. So like that. Then when I try to put a 2 here, and I will go up, sum of these two values becomes 5, go up, sum of these two values becomes 5, and sum of these two values become 5, like that. So you will realize that every time you update a node, you will need to change the values of only login nodes. That is why updation will also cost you login time only. Okay, so that was the whole idea of segment tree, and now we will try to implement the segment tree using C++. Okay, so let's see how we can do that. Okay, this was the code of our last prefix sum algorithm, and now since we want to create a segment tree, okay, let's see. Okay, we have this. Now what I can do is I can maintain a left and right child. Like if I am at ith node, this will represent 2 times I, and this will represent this node will be represented by 2i plus 1. Okay, so if this is the case, like since this tree will obviously be a binary tree, we can simply use an array to represent this whole tree. Okay, so how do we go about this? Let me think about it now. Okay, so since I'm trying to implement this, how can I implement this? Okay, so obviously I will need a node value. So let's say struct of node. So let's have a node value, a node struct, and will have a value. Now you can obviously use, you do not need to create an array of node. You can strictly use an array of integers, but just to keep things general, because sometimes segment trees have multiple values in their nodes, and sometimes we have to make 2 segment trees instead. So just to avoid that, and to keep things general, I'm using a struct here. Okay, and let's have long min as, not long min, let's have a 0 here, because we are trying to make a sum query, not the maximum minimum query, right? So let's have value equals to val. Sorry about that. Okay, so we have this. Now what we need is, I want to create a vector of node, right? And this will represent my tree, and obviously I need a size, and let's have a void build function. So this function will actually build my segment tree. Okay, now to build the segment tree, what do you really need? Okay, why is it giving me errors? Because I did not put a semicolon here. Now when we are trying to build the segment tree, what I want to do is I want to pass in my vector here. So let's say vector int and array. So let's take the size of this vector first. Okay, and now that we have the size, I want to find out the size of the segment tree, like how many leaf nodes do we have. Do you remember I said that, okay, I erased it, but I said that, okay, let the number of leaf nodes is equals to size sz. Okay, and the length of this segment tree is approximately 2 times sz, right? Just to have a complete segment tree, what you can do is you can actually simply make it 4 times the length of the array, and that will suffice, but I like it doing this way. So this is my implementation. Okay, so we have this. Now let's say int size equals to 1. Okay, size equals to 1, and obviously for n equals to 1 case it will give me a wrong answer. So let's say if n equals 1, then size will become 2. Okay, and we have that. Now what we were doing is like till the number of leaf nodes were just greater than this number, the number of elements in the array. We were actually multiplying this by 2, so the number of leaf nodes increased by 2 times at every level. Okay, so what we can do is while sz is less than n, sz is equals to 2 times sz. So that is how we increase the number of levels, and then we can say like tree dot assign. So that will resize my tree array, so 2 times sz, and initially I want to have the default value, that is node, right? Okay, so we have that. Now okay, now let's try to what can we do? Like for I range this, I want to do something to assign it. Now this is easy. Like what I can do, simply say is tree of I plus sz equals to node of array of I, and then I can simply like keep dividing my I, and that will happen. Like okay, instead of doing it this way, first I want to show you the recursive implementation. So let's try to do this recursively. So let's say we have a node. What I'm trying to do is I'm trying to do some point updates, right? So let's say node point update, and it is taking position int and position value, and on this position and on this value I want to update the segment tree. So I will have int node, int which is by default equals to 1, int node low, and this was 0, and int node high, this equals to sz minus 1. Okay, so when I am starting from this position, right? So whenever I am starting from this position, when I'm trying to when you want to update this, what you can do is like I'm always starting from the root node. This has node value 1, so I try to go left and try to reach this position where the I and I both are equal, right? Where the node low and node high both values are equals to the position value. So what we can do, like first of all, if my position is less than node low or the position is greater than node high, obviously what I want to simply return is the tree node. Okay, I don't want to do anything, right? In the else case, like when we have both the things equal, so position equals the node low, and position equals node high, what we can do is simply why is this giving me error? Okay, it should be small n, sorry about that. Now when we reach this position, like I went some zigzag manner 1 2 3 like this, and I have reached the base leaf node. There are no more nodes. Okay, so when I reach this node, I just simply want to update this value. So I can say return tree of node equals to, and I will assign it a new node with the value of what should I say, like with the value of val, right? And now let's say I did this, and now I went up, I need to update the value of this node, right, by as the sum of these two values. So I can say like okay, actually let me write a combine function. So let's have a node combine function instead. So it takes in node A and node B, and it will return a new node that has the value a dot value plus b dot value, right? So this will return me a node, and then let's calculate the mid value, that is equals to what? How do you calculate the mid value? Mid value is simply the node low plus node high by 2. So node low plus node high, and then you simply divide this by 2. And then remember, we need to update this value. I'm going to go left and right, and then after coming back I need to update this value. So what we need is, I'm simply going to return tree of node equals to combine point update what, let's go left and then let's go right. So first, when we want to go left, I'm going to say like position and value, these two values will not change. This will change like 2 times node, so I'm going to the left direction, and this will become node low comma mid, and then again point update position value, and this will become 2 times node plus 1, that is the right child, and then this will become mid plus 1 to node high. Okay, so that is our point update function. So we went left and like that, and whenever we got back, I updated the value of this node. So this is the recursive way to do this. I will also show you the iterative way, but for now we have this. So we get the point update I comma array of I. Okay, so we have this. Now I will just show you how just show you how to actually print this. Now for now, let's comment this whole thing. I don't need this, I don't need this, I don't need this. Okay, so I will try to say like, okay, let's have a build of A, and now for I in range n, cout, let's say tree of I dot value with a space. And when we run this, like when I run this, and here you will see that we have this array 24 14 10 0 5 8 9. Okay, I don't have it written, but I think this is correct. The leaf node represents these values. Wait a second, I think we made some mistake. 24 looks correct. Oh sorry, it should be sz, not it should be 2 times sz, not like this till n value. Sorry about that, even I make mistakes. Now yeah, we have this. So these are the leaf nodes, and what you will see is that we have 8 plus 2 is sorry, these are the leaf nodes. So 3 plus 2 is 5, so this is 5, then 5 plus 4 is 9, we have 9 here, and like that we have this. Okay, so what we can do is, instead of going recursively, like this is the recursive implementation, what you can simply try to do is, you can try to do this iteratively. Like how, I'll just show you. Let's say, and what you can do is position plus equals to size. Like, since let's say you want to have a position at position 1, okay, so this is position 1, but in this tree array it will be represented by the position plus size, like 1 2 3 4 5 6 7 8 9, because size was 8, this sz value was 8. This value, when you start counting from 1 2 3 4 5 6 7 8 9, so this value is represented by position plus size. Okay, so we have this as 2. So now you can simply say tree of position equals to node of value. Okay, and then while position is greater than 1, you can simply say position equals to position by 2. So you are going, every time you divide it by 2, you go one step up, right? And then you try to combine these. So tree of position equals to combine tree of 2 times position, the left and right child, 2 times position comma tree of 2 times I'm not sure what I'm doing, but yeah. Okay, So we have this. Now even if I run this again, it will give me the same output, I think. What is happening? Okay, let's make this a void function now. Yeah, so we have the same output basically, and this implementation will be a bit faster than the recursive one because recursive has some unnecessary function calls. So we have this point update function, and yeah, so I think this works. So this was how you can build your segment tree and how you can point update in your segment tree. Okay, we will not go into range updates in this video. It will be discussed in when we have some uh, lazy propagation also. But for now, let's keep things simple and let's try to do this. Now we have this point update function. Now, since we have built our segment tree, it is time to query from it. So let's say while q minus minus and lnr. Obviously, I want to do make them zero based indexing first, and now I want to query. So let's say we have node range query int l int r. Okay, and similarly we can query it using the recursive way, like int node equals to 1, int node low equals to 0, and int node high equals to size minus 1. And like, okay, when I will try to go more left, right, left till I have some value. So like if my L is if my low is greater than node high, then there is no point in going further. If my R is less than node low, then also there is no point in going further. So I simply return the node of 0. Like I don't really need to go any further. I've simply return a default value because this value, this one is completely outside the range that I want. Okay. Now, if this is not the case, then if we have L is less than, sorry, if L is greater than equals to node low and R is less than equals to node high, so this value is completely inside the range that I want. So I will simply return the tree of node, right? Otherwise, I will simply calculate the mid value. That is, how do you calculate the mid value? Mid value is simply node low plus node high, and then you can simply divide this thing by 2, right? And once this is divided by 2, you can do the same thing. Like what you need to do is you need to simply return the combination in the left and right. So range query, let's go left first. So these two values will not change, L and R. What changes is first you go to the left child, so it becomes 2 times node, and then you go node low comma mid, and after that let's say range query, then L and R, and then you go to the right child, so it will become 2 times node plus 1 to mid plus 1 to node high, right? So this is how you can query it, and this will run in your login time. And now you can say, okay, cout range query L to R, and obviously this is returning the node, so you need to print value, right? Yeah, let's try to run this and see if it gives us a segmentation fault. Okay, it is giving me 24 24 24, which is wrong. Why is that? It should not have been like this. And okay, now L is okay, so I think this condition is wrong here. So when do we have a complete we have a node low value, so let's say I want this value. So when do we want to, I have a node low and node high. Okay, So this node low, like L value should be less than equals to node low, and the R value should be greater than equals to node high. So this is what I want whenever I want to directly return upward. So if L value is greater than equals to, sorry, L value is less than equals to node low, and the R value is greater than equals to node high, then I want to return it like this. Okay, so we have the exact answers here, and if we try to submit this, it is going to pass. But what you will see is that this is a recursive implementation, so obviously it will be slower than the iterative one. So I want to query this iteratively. Okay, so for that, first of all, I'm going to say like L plus equals to size and R plus equals to size. Okay, okay, so let's say we are here, and okay, I think it will be a bit difficult, but bear with me. Okay, so let's say we have some L and R values. We have L here, we have R here. Now how do we calculate this thing recursively? Clearly, like, okay, let me just try to make a new figure. So let's say we have this, we go left and we go right. Now when you want to query, like, let's say this is our L value and this is my R value, and for the ith node, the left child is represented by 2i, and the right child is represented by 2i plus 1, right? So this is my so if your okay, so if your L value is this, does it make sense to, and somewhere very far away you have an R value? Okay, let me just let's say somewhere very far away you have an R value. So if your L value is, obviously if L value is even, okay, does it really make sense to take this value? No, right? Because you can simply, because this node contains the sum of these two nodes, right? So it makes sense to actually divide this by L by 2 and take the sum of this value, right? So if L is even, so if L mod 2 equals 0 divided by 2, so L gets divided by 2. And similarly, let's say I have two childs, let's say 2i and 2i plus 1. And now if my R value is odd, right, does it really make sense to you know if my R value is odd, does it really make sense to take the sum of the value of this node? No, right? You should divide this by 2 because this node will have the sum of these two nodes. So that is what we will try to do here. Okay, so let's say while L is less than equals to R, and now if the L value is odd, then we will take it. So let's also maintain the final answer, so node res. So here if my L mod 2 equals 1, what I'm going to do is I'm going to combine the res value and L. Okay, so let's say not tree, sorry, res equals to combine res comma the tree of L. Okay, and once this is done, obviously I should do an L plus plus. Now why L plus plus? Because if my L value was odd, I took this, and then I don't want to get the sum of this the value in this, because this when I divide this by 2, this will point to this parent. But what I want to do is I want to go in the next segment, that is 2i plus 2, and this will point to the parent that has I plus 1 as the parent, right? Because I didn't really need this child anymore. Okay, so I said like, okay, L plus plus, and similarly I have to check, like, if R mod 2 equals 0, I will say like res equals to combine res comma tree of R. The same case, and in here I will do R minus minus instead of R plus plus, and in the end I simply have to do L equals to L by 2, and r is equals to r by 2, and that completes the function. I think I also need to return the res also, the response, right? And in this case, since we are doing the iterative version, we don't really need this. And I think if I run this code again, it should give me the same output. Yeah. Okay, so we have this the segment tree implementation. Okay, so I hope you were able to understand this. Let's try to actually submit this and see if it passes all the test cases or not. So your static range sum queries, submit, and a solution got accepted. And I mean the time difference is only 0.04 seconds, so it doesn't really matter much. Both the prefix sum and this segment tree approach will work. And I hope you were able to understand this segment tree way of doing things. And in the next video, I will try to solve the same problem using square root decomposition. Okay, so I will see you guys next time. Thank you.